thanks for inviting me to this conference. So I guess at some point we'll see some slides, but anyway, this project is about thinking about the evaluation of nonlinear DSGE models. Is joined with Borana Aroba and Luigi Boccola. A lot of the empirical work, in particular the econometric work in the DSGE model literature, has been done with linearized versions of these dynamic stochastic equilibrium models. For these linearized models, vector autoregressions have been a very natural benchmark. And so, people asked, does the response to a monetary shock or a technology shock that's generated by a DSGE model, is that similar to what we get when we look at impulse response functions for vector autoregressions? There are many ways of implementing this basic idea econometrically, and what we want to do is we want to ask, well, suppose that we actually replace the linear solution of the model by a nonlinear solution, and look at models which may have some interesting nonlinearities. Are these nonlinearities sort of commensurable with what we would find if we had, say, a nonlinear version of a vector autoregressive or autoregressive model? Of course, there are lots of nonlinear time series models, but looking around, we didn't really find one that's particularly natural, given the kind of nonlinearities in DSGE models we wanted to look at. And so we set out and proposed a new class of time series models. And they try to mimic the kind of nonlinearities that arise in DSGE models when they're solved by perturbation methods. And so we want to use these as a benchmark for evaluating DSGE models. Now, ideally, we want to do this in a multivariate way, but so far we've taken small steps, and what you'll see is you'll just see results from univariate versions of these nonlinear time series models. So basically, what I'll do is I'll talk you through these what we call quadratic autoregressive models. I'll tell you a little bit about how they're set up and why they're set up that way, what their properties are, and how you can estimate them, and then we basically use them to construct what's in the Bayesian literature called a posterior predictive check, but it's sort of it's sort of something intuitively quite simple, and we'll apply that to a small-scale New Keynesian DSGE model with asymmetric price and wage adjustment costs. So basically, the question that these predictive checks ask is, well, suppose you estimate these quadratic autoregressive models based on model-generated data, and look at the estimates. Well, do they look like estimates that you would get if you were to use US data? And then there's a way of formalizing this basic idea, and we formalize it using these posterior predictive checks. So I'll talk about that, and in the end I'll give some summary and outlook. Okay. All right. So let me just give you some idea of what nonlinearities we often generate when we use perturbation methods to solve DSGE models. So what you see here is basically, it's supposed to be a generic solution to a dynamic stochastic general equilibrium model. So there are some control variables. So think of consumption or investment, and then there are some state variables. The state variables are divided into exogenous state variables. Think of total factor productivity, and endogenous state variables. Think of the capital stock. And so what you usually do is you specify some law of motion for these exogenous state variables, which often is just a linear autoregressive processes. Well, if you do a linear approximation of the equilibrium dynamics, what you would basically say is that while the endogenous state variables evolve as a linear function of lagged endogenous and lagged exogenous state variables. So there's a slight typo here. And then the control variables are linear functions of the state variable, of the current state variables, the way the system is written here. And so, basically everything in black is sort of your typical linear solution. And what higher order perturbation methods basically do is they generate additional terms. So you have some quadratic terms. You could have third order terms if you do a third order perturbation, or fourth order terms, and so you get these additional terms here. And then you tend to relate the model variables to some observed variables using some measurement equation. The main point is that if you make a comparison to a vector autoregression, then you don't really capture any nonlinear dynamics that the model captures with these higher order terms. Okay, and so what we want to do is we want to think about time series models that that have these terms in there as well. All right, so let me just run through how we do this, and this is also gives you a description of how to think about these perturbation methods and what they do. So think about the following. Think about so this is now just a simple backward-looking system. An autoregressive system, so y depends on yt minus 1, and then there's some shock ut and a shock standard deviation sigma. And so in general, the idea of perturbation approximations is basically, well, we want them to get accurate as sigma goes to 0. And so the way you could do it is you could say, well, there's the solution is going to be linear, has this kind of additive form, and there's basically a part of the solution that's of order sigma to the 0. There's a part of the solution that's of order sigma to the 1. There's a part of the solution that's of order sigma squared. And then there are other terms that go to 0 faster than sigma squared. Okay? And then what you can do is you could say, okay, let's take a Taylor series approximation of this f function, and then we'll just plug in this guess of our solution, and we'll try to figure out what these components are. Okay, so that's basically, and then you get this kind of colorful slide, which looks really complicated, but it's not all that complicated. So the first thing that you see is basically a Taylor series approximation of this f function. So you see these derivatives with respect to y. With respect to u, second derivatives, cross derivatives, and then we've plugged in this solution, and then there are all these terms. And so some are green, those are of order 0. Some are blue, they are of order 1, and some are red, and they are of order 2. And then you just say, well, okay, let's just collect terms on the left-hand side and the right-hand side, and you kind of start equating things. So, stuff of order 0, of order 1, of order 2, and then you're in business, because now you can get a law of motion, an autoregressive law of motion for the terms of order 1 and for the terms of order 2. And this has a very nice structure because it's recursively linear. Okay, So if you look at the evolution of the second order terms, they linearly depend on past second order terms, and then everything that's nonlinear sort of comes from the first order terms. And the evolution of the first order terms is your usual AR1 process, and then there's a constant term. And so then you can take all of this and basically put it together, and you get a time series model that basically looks like this. So there's yt, it's a function of yt minus 1, just like in a usual AR1 model. And then there is this quadratic term, and the quadratic term basically is sort of the square of some hidden process that captures the dynamics in a first order approximation, and that's this thing here. And then there is some interaction between st minus 1 and ut, and in principle there would be another term, ut squared, but we leave that out to basically maintain some conditional Gaussian distribution here. And so now you could look at this and say, well, you know, how does that compare to something I know? So first of all, well, if this gamma guy is 0 and the phi2 is 0, then you have your standard AR1 model, right? Second of all, you know, if you kill this quadratic term, then it turns out, you know, it maybe looks similar to a bilinear model, or what's called a linear arch model. You could also say, well, you know, this was really complicated. Why did we have all this, go through all this perturbation solution? Why can't we just put yt minus squared in the equation and then run with that? Which would be what Stefan Mitnick called generalized autoregressive model. And the reason is that, well, you know, this sort of looks intuitive, but has some pretty nasty properties, in the sense that it has multiple steady states. So you have a quadratic equation here. So there are two. You know, it has two roots, and it has certain explosiveness. So if you get hit by a large shock, you might get pushed into an explosive region of the state space. And if you look at impulse responses, they're just off the chart. So you wouldn't even see them on your in your plot. Okay. And so now we can run through some properties. The nice property is really that it's recursively linear. So, you know, if you define z as st minus 1, st minus squared, and ut, you can just approximate it basically as a moving average of some nonlinear function of this vector here. And then you can also, you know, pretty easily figure out what the stationarity restrictions are. And it inherits the same restrictions that you would put on the AR1 model, right? So as phi1 is less than 1 in absolute value, the whole thing is strictly stationary. If you're into Volterra representations, you can basically express yt as a function of the past uts and quadratic terms in these uts. So there are no higher order terms in this Volterra representation. You can calculate its moments. It's relatively straightforward because, you know, you can figure out, you know, all the moments of this AR1 process, and then yt is sort of just a function of st and st squared, and so again, using this recursively linear structure, you can calculate all the moments. So that's nice, but you get richer dynamics than from a regular autoregressive model. So you can have some conditional heteroscedasticity. Impulse responses would depend on the sign of the shocks, on the size of the shocks, on the initial state st minus 1. So all the kind of things that we like from nonlinear models. All right. Well, you can if you condition, at least if you condition on the initial states, you can calculate the likelihood function recursively. It's a so-called observation-driven model. And you could do Bayesian inference, for example, using a Gibbs sampler or some other Bayesian computational methods. Okay. So this is our benchmark time series model that we use in the assessment of the nonlinearities in the DSGE model. Okay. And again, as I said, we're interested in multivariate extensions. I mean, obviously, you look at this, you could go different directions, right? You could add more lags, keep it univariate. You could, instead of doing second-order dynamics, you could do third-order dynamics. One of the things that you run into is sort of a proliferation of coefficients. So if you wanted to estimate a multivariate version of it, you'd have to think about carefully about some shrinkage methods or so that introduce some parsimony. Okay, so that was this time series model. And now what I want to do is I want to talk about a DSGE model, which potentially has some of these nonlinearities that we can capture with that time series model, and then we'll see what we get. So the first time we just used a simple standard 3-equation New Keynesian model. And well, for those of you who've worked with this model, you know that the decision rules in that model, unless you're close to the zero lower bound, they're basically linear. Okay, and so then the way this predictive check looks like is you have a model that doesn't really generate any nonlinearities. We're going to pick up some nonlinearities in the data, and then we've learned that well, the model hasn't generated any, doesn't really reproduce these nonlinearities because it didn't have any nonlinearities to begin with. Now, so in the second iteration of this process of looking at various models, we basically said, okay. Let's use some ad hoc way of introducing some nonlinearities, and this would be we could have asymmetric wage and price adjustment functions that capture some nominal rigidities, but they can be potentially asymmetric. At the same time, they generate some cross-coefficient restrictions in these nonlinearities, so it's not as obvious as from our first experiment of what comes out of the empirical analysis. So the most important equation then is this adjustment cost function here. Think of x as either prices or wages, and I'll show you a picture of this function in a couple of slides. The rest of the model is a pretty standard New Keynesian model in which we have households with intermediate goods producers, final goods producers, and a central bank and fiscal authority. So the final goods producers, they basically buy these intermediate goods and aggregate them into a final good. The intermediate goods producers here just use labor as an input, and so they hire labor. The production is sort of subject to this stochastically changing technology process. And we have these price adjustment costs, so these intermediate goods producers, where basically they face a downward sloping demand curve that comes out of this aggregator here. Unlike what you've seen in the previous paper where there was this SS policy, here we assume just convex, quadratic price adjustment, Linux price adjustment costs, which are in terms of output. On the household side, basically, the key is that we have a continuum of households. They provide differentiated labor services, and you know, each of these households or workers, they are monopolists with respect to the labor service that they're providing, and you know, they have this cost to adjust their wages, which again is asymmetric. And then there's, you know, you aggregate the labor services, and then this aggregated labor is being used by the intermediate goods producer. So that's the structure, sort of a common way of introducing wage stickiness in these new Keynesian models. There's a fiscal authority which taxes households, consumes a fraction of the final output. There's a monetary authority which basically determines the nominal interest rate in response to inflation and output growth movements, and there's a monetary policy shock. So, you know, overall we have 4 exogenous shocks: technology, there's sort of a general demand / government spending shock G, there's a price markup shock, lambda, and then there's the monetary policy shock. So that's roughly the description of the DSGE model. Okay, so it's pretty standard, except for these asymmetric wage and price adjustment costs. So what we do then is, well, you know, we take data, GDP growth per capita, nominal wage growth, inflation, and the federal funds rate. We pick an estimation sample. So we've done, you know, a lot of different samples, but what I'll show you is 1984. So post-Great Moderation until you know, the onset of the Great Recession. The reason we're leaving out the Great Recession is it generates these you know, to reconcile the data with a model like this, you would need these huge shocks, and you know, we didn't want to have that contaminate our estimation. We do Bayesian inference. You know, we take a second-order perturbation to solve the DSGE model, and then we use a particle filter to evaluate the likelihood function, sort of stuff that's by now fairly standard. And I'm not going to talk much about the details on the prior and the posterior distribution that come out of this estimation. I just wanted to show you this adjustment cost function. So price adjustment cost and wage adjustment cost. So these are the estimated cost functions. You basically see 3 of them. So initially, we wrote down this Linux function, right? And then I said, well, I'm going to do a second-order perturbation to solve the DSGE model. Well, if you think about how do these cost functions enter the equilibrium conditions, of course, you know, what matters is the derivative of the first derivative of the cost function. And then if you do a second-order approximation, that basically puts you to, you know, effectively you're using a third-order approximation of this Linux function. So Linux is green. Oops, sorry. The third-order approximation is red, and the second-order approximation would be blue. Now, the blue thing would just be a symmetric price and wage adjustment cost function, which is what, you know, people typically use, and the red one is basically this third-order approximation of the Linux function, and you could see. So these 2 lines here, this is basically, you know, the region of the state space that the model tends to visit, and in that region, you know, this approximation is pretty good. Of course, you know, what's going to happen if you had very large inflation or wage changes, you know, this thing, you know, would come down eventually, and this whole third-order approximation wouldn't really do what you wanted it to do. But over in this range here, it's pretty reasonable. All right. Okay, so that's the and you know, you can see that there's some mild form of asymmetry by just looking at the deviation of the red line from the blue line. All right. So that's the estimated DSG model, and now we said, well, you know, what we really wanted to do is we wanted to use this this autoregressive model to learn this QAR model, to learn something about the extent to which there are nonlinearities in the data, and the DSGE model actually captures these nonlinearities. So that's the ultimate goal. And so, as I said initially, we're using these posterior predictive checks to do that, and this is kind of how it works. So, you know, we've done this Bayesian estimation of the DSGE model, which means that we have all these draws of DSGE model parameters theta stored on our hard drive. And for each of these draws, theta m, we're going to simulate trajectories of output growth, inflation, the nominal wage, and the interest rate, using the same length as in the actual data, and we simulate that from the DSGE model. And then based on these simulated trajectory, we can calculate sample moments, and we can compute posterior mean estimates of the QAR11 parameters. You know, since we have, like, you know, 100,000 of these draws, we do this 100,000 times, and then we have 100,000 estimates of these QAR11 parameters, and we're just going to draw densities, and we have the estimate that we've obtained from US data, and we'll just see how far that's in the tails. Okay, so let's do that. Okay, so here's a picture. So you may not, from where you're sitting, you may not be able to read all the legends here, but I'll walk you through it. So the first thing that you should see is there's a blue line here, blue density, and then there are these red vertical lines, and then sometimes you see a blue density and a dashed black density. Okay, so the blue density is generated using simulations from the nonlinear model. We've also estimated just a linearized version of the DSGE model, and the black dashed densities are generated by simulating the linear model. And then we have the data, because everything that we can compute on actual data, we can compute on simulated data, and vice versa. And so the red line just indicates the actual data. And so here what we, you know, this says, you know, linear statistics. So the first thing we do before going through the QAR analysis, we say, okay, let's just see whether the sample mean that we see in the data for output growth, which at a quarter-on-quarter rate is 0.5%, so, you know, roughly 2% annually. That's the red line. Whether, you know, the estimated model, when you simulate data from the estimated model and you compute the sample mean, whether you get something very similar. And of course, there's uncertainty in the estimation of the sample mean, and there's sort of this variation that comes from you know, using different draws of the DSGE model parameters when we do the simulation. And so we get this distribution, but it's basically centered around 0.5, right? And whether you do that with the nonlinear model or the linear model, you know, it's going to be the same. And then, you know, we can do that for the mean wage growth, for the mean inflation rate, the mean interest rate, and, you know, it's sort of, these models, you know, capture the mean, okay? and then we do this for the standard deviation of output growth, wage growth, inflation, and interest rates, and it sort of works out as well. Okay. You know, maybe not so much over here. There's a little bit. We're a little bit further in the tails, but by and large, it works quite well. And whether we use the linear version or the nonlinear version of the model, it's sort of very similar. So then, you know, next thing is, well, you know, what if we pick some correlation instead of just means and variances? So here's some correlations. Again, I apologize for the slightly small labels. This is the correlation between output growth and nominal wage growth. Sort of zero in the data. It's slightly positive in the model. So we're not doing too well in this dimension. You know, here's sort of the persistence of inflation, zero correlation of inflation. There we're doing pretty well. Zero correlation in interest rates. The models kind of have, it's very high in the data, and the models have some problems generating that. But sort of, you know, by and large, it works, and there's not a huge difference between the linear and the nonlinear model, though in some of these correlations there is a difference. So now let's try something, you know, quote unquote nonlinear. Let's look at skewness. And so here, you know, you compute the skewness in inflation rates, and you compute the skewness in the nominal wage growth, and you could see that it's noticeable in the actual data. And you can see, of course, you know, the linear model is sort of dead in the water here because it's a linear model. It's driven by Gaussian shocks, so nothing is happening here. But at least the estimated nonlinear model is able to capture some of the skewness in the wages and some of the skewness in inflation. So the nonlinear model is able to capture some of the nonlinearities here that we seem to see in the data. So up until this point, I've only used basic sample moments, and now I want to see what happens when we look at these QAR estimates. Okay. So, you know, the first thing we're going to do is we'll look at the QAR11 estimates obtained from US data, and then we compare them to the distribution of estimates generated from simulated data. So I'll talk a little bit about what we find in the US data, and then I'll tell you, you know, whether the model can generate that or not. Okay. So here's, you know, it's Bayesian estimation. We need a prior distribution. Yeah, I guess the key features is that we use a pre-sample from 57 to 83 to basically center our priors for the linear part of the QAR11 model, so for phi naught, phi 1, and sigma. And then we have these parameters that capture the non-linearities. Phi 2 was basically capturing the, you know, lagged, sort of think of it as yt minus 1 squared, and the gamma was capturing the interaction between yt minus 1 and ut. Okay, so this is, you know, these quadratic dynamics, and this is like, you know, conditional heteroscedasticity, and they all are centered at 0. So here's what you get when you do this for GDP growth. You get a phi 2 that's slightly negative, minus 0.13, and you get a gamma that's slightly negative at minus 0.05. And then you could say, well, you know, suppose so, you know, there's a little bit of if you compute a credible interval, it sort of seems like 0 is included. So what if we do a posterior odds comparison of the QAR model versus the AR model? There's a slight evidence in favor of the QAR model. So these are log values. So you think of differences in these as log odds. So something like e to the minus 2 are the odds in favor of the QAR11 versus the AR1. So, quite small actually. There's some evidence of these nonlinearities, but it's not super strong. Anyway, what do you pick up? So this is just a scatter plot of lagged GDP growth on current GDP growth, and then there are all these observations, and then there's just a linear regression line and a quadratic regression line in this plot, and this is kind of what you pick up with these coefficients. And so I guess any of these these types of nonlinear models, when you estimate them, of course they're quite sensitive to extreme observations, which is why we excluded the Great Recession from our estimation sample initially. Here you have the path of GDP growth in blue with the two recessions in the early 90s and the early 2000s that are included in the sample, and this red is this sort of hidden state ST, which kind of tracks the first order dynamics of the process that we're estimating, and it, of course, it pretty closely tracks the GDP growth, except it's centered at 0 by construction, whereas the GDP growth has its mean of 2% annually. So then, this phi2 basically says that, well, so the phi2 is negative. So basically, if you have you can calculate, for example, the effect of this is like a impulse response function after one period. So the marginal effect of a change in ut on yt plus 1, and you could see that, well, phi2 is negative. And ST, if you think about bad times as ST being negative, so your growth rate is below average. So this one is negative, that one is negative. It basically leads to an amplification of this negative shock UT, and you could see that basically the shocks push you down in these recession periods because of the negative phi2. You can calculate, these are univariate models, but it just traces out the response to a shock in UT, conditioning on either large negative STs or large positive STs, and then looking at positive shocks versus negative shocks, but flipping the sign on the negative shocks so you can compare it. So what you see, the difference between here and here is basically comes about through this negative gamma. So the shocks are sort of, when they push you down, they well, if you're in a bad state, the effect of the shocks is more pronounced. And the phi2 being less than 0 basically implies that negative shocks tend to be more persistent than positive shocks, which we saw in this representation here, and they led to these fairly drastic drops in GDP growth. Now, we can calculate the conditional variance. Due to this gamma here, it's not constant, it's varying over time, and it's marginally larger in these recession periods, but really just very marginally, because the gamma is relatively small. So qualitatively it goes in the direction that output growth volatility increases in recession, but quantitatively what you pick up with this model isn't particularly strong. So finally, let's go to the predictive check. So again, what we're doing now is we estimate, we've estimated the QAR model on US data, so we're still looking at GDP growth here. The the red lines represents the estimates that we just talked about. So, you know, let's focus on phi 2 and gamma. So that was minus 0.13, and that was roughly minus 0.05. And now the question is, well, if we generate, if you simulate data from the model, what kind of estimates of phi 2 and gamma do we get? And what you see is that even though, you know, the model has some asymmetry in the wage adjustment cost functions and the price adjustment cost function, you know, that doesn't translate into any non-zero estimates of phi 2 and gamma when you do the estimation of this QAR model on model simulated data. So, you know, basically, you know, the model can't produce these negative estimates of phi 2, in particular of phi 2. Okay. Whereas, you know, for the phi naught is basically, that's the mean or steady state of the system. This was the standard deviation of the innovation that works quite nicely. And here the estimated model doesn't generate quite the persistence in GDP growth, but that's sort of something that we know from this class of models. So now we do the same thing on on wages. Since, you know, we've been talking about downward nominal wage rigidity, so we get a negative phi 2, and we get a positive estimate of gamma, and again we sort of get a mild evidence in favor of these nonlinear dynamics. This is sort of the same picture as before. I mean, you know, again, what you're doing is when you include these higher order terms, instead of, you know, fitting straight lines, you're fitting quadratic lines. So let's look at the these phi 2 and gamma again. And so here, you know, we're successful in the sense that from the data we're generating a negative phi 2 estimate and a positive gamma estimate. And if we do this on model simulated data, you know, you see that this density here is sort of shifted. This one is shifted to the left, and on average, or the median estimate of phi 2 based on model generated data is pretty close to this minus 0.08, and the same thing here. We're able to, you know, at least shift the density a little bit in the right direction. And so, you know, this is just highlighting a little bit more this predictive check for nominal wage growth. So, you know, the blue line corresponds to, you know, doing the simulation with exactly the posterior estimates of these asymmetry parameters. The green line corresponds to, you know, taking the same estimates but setting the asymmetry parameters equal to 0, and the black line corresponds to making the asymmetry parameters a little bit larger. And again, the red line corresponds to the estimate obtained from the data. And you can see, if you look at phi 2, for example, if you shut down these asymmetries, you know, this predictive density basically shifts to the right, you know, closer to 0. It's not centered at 0, so even without these asymmetric adjustment costs, there seems to be a little bit of asymmetry being generated in the you know, with a second order perturbation method, but not as much as if you have these parameters. You know, if you increase the asymmetry, then, you know, things shift outward, and, you know, to a similar extent, it's happening for gamma as well. Okay, so let me skip this. You know, we could have done a similar. This is a similar chart generated for the skewness in nominal wage growth and the skewness in inflation. And you can basically see that you know, these parameters here, this the asymmetry parameter and this Linux adjustment cost function, you know, basically shift you shift the model in terms of in the right direction in terms of being able to generate some of the asymmetries that we see in the wage and you know, to some extent in the price series here. So in the paper we have we have these predictive checks for inflation and for the federal funds rate as well. But let me just wrap up in the remaining minute or so. So you know, if we look at you know, estimated DSGE models, then you know, we've basically brought them to a point where I think they produce reasonable first and second order moments, but you know, when we use nonlinear versions of these models, it's not clear that the nonlinearities that these models generate are in fact the nonlinearities that we have in the data. And so I think, you know, we need tools to check that. And so, you know, we've learned a lot from comparisons between VARs and DSGE model and linear DSGE models, or at least or even nonlinear DSGE models, to what extent they capture, you know, basic order covariances. But more of that is needed for nonlinear DSGE models, in particular now that we're using them to think about the crisis. Which is sort of, you could think of as you know, a large non-linearity maybe. And you know, what we see in this empirical illustration is that, well, in some dimension, the DSGE model, the nonlinearities in the DSGE model and in the data kind of lined up. So in that respect, I think, you know, looking at the wage growth, nonlinearities in wage growth, nominal wage growth, and inflation was sort of a success. And with respect to output growth, it didn't work that well. So the model wasn't able to generate the kind of nonlinearity that we seem to pick up in the with this QAR model in the actual output growth data. And so, as I said, what we like to have is a sort of an extension of this to a vector autoregressive framework, so that we can you know, look at the propagation of shocks in a multivariate system, and nonlinear propagations of these shocks, and see whether we can match that with our models.
So we have time for perhaps 2 questions. All right, so, okay.
Mark Watson. So I understand you got these densities, right? And those are densities of data given the sample data that you saw, right? That you sort of then pass through the model. You know, those give you posteriors for the parameters, right? And then you've got sort of then some sort of like marginal density of data that you would expect to see if you could get an independent draw from what you saw, right? But then you put the actual data in, those red lines. So how do I think about the red lines and the blue densities? I'm just confused with the basic.
It's sort of like introducing you know, somewhat frequentist ideas into a Bayesian framework. But you know, the idea, it's sort of a tool of doing model diagnostics, right? And it just says that, well, you know, if my model, so you know, in a Bayesian way, you could do model comparisons 2 ways. If you have multiple models, you can compute odds, and that's sort of one way of doing it. If you have if you're interested in a particular model like this DSGE model here, then you could ask, well, you know, now we've estimated it, and you know, does the estimated model produce data that in any way look like the actual data. And so, just like in a, in a general specification test, you would sort of look at whether, what you observe in the data is sort of likely or very unlikely under, under the model that you're entertaining here. And, in the frequentist framework, you sort of push that all the way to a hypothesis test, and here in this Bayesian framework, it's sort of used more as a diagnostic. But if the actual estimate, based on the actual data, or the sample moment or this QAR parameter estimate lies very far in the tails, you would say that, well, there seems to be something very different in the actual data and in the model generated data. And so you try to learn something about in which directions things line up. So for example, in terms of means and standard deviations, things seem to line up. Between the estimated DSG model and the data that was used to estimate it, and with respect to some of these nonlinear features that we found in output growth, it didn't line up. And with respect to the nonlinear features we found in wage growth, it did line up.
Marty, and then João, that's our list.
Sure. Just a general philosophical question, which is, you could estimate, I mean, in the linear VARs, we were interested in sort of some structural interpretation of the innovation, but that's of course not the spirit here. There's just some moments of the data that wouldn't be of interest in a Gaussian world or linear Gaussian world, but they are of course possibly there. So should I think really that the nonlinear VAR is just a parsimonious way of estimating those moments? I could just estimate those moments and then ask whether my model gets them.
Yeah, so that's right? I mean, so, if you do a comparison to a VAR, so instead you could just, calculate all the sample autocovariances, and, you might have 100 of them or so, and see whether the model gets them. And so mechanically, that's exactly right. I guess the reason that we do the transformation, say, into impulse response functions or coefficients of a vector autoregression, but I mean really impulse response functions we know kind of how to interpret, and we feel like we learn a lot from that, is because it's easier to think about those than just 100 sample autocorrelations, and so ultimately that's the direction that we want to go. We're not quite there yet because we don't have the multivariate analog so that we could basically compute impulse response functions and then say, well, is the propagation of a monetary policy shock, is there nonlinearity in that propagation that we can or cannot capture with our nonlinear DSG model.
So I got a little bit confused, but you did in-sample model comparisons. Is that what you've done? An in-sample evaluation?
Oh, sure, yeah.
So if that's what you've done, out of sample.
I just wanted to explain why Frank said this was sort of a frequentist thing to do. Frequentists sometimes have the illusion that they can test models without specifying an alternative, even though Neyman and Pearson would never have suggested that. The densities that Frank showed, if I'm allowed to make monotone transformations of the quantities whose densities Frank was plotting, I can make the peak of the density appear anywhere. So the tails are totally dependent on the units of measurement of these things. The legitimate way to use this kind of model check is to have more than one model and see if one of the models can get the observed data to be at a higher posterior density point than the other. It doesn't really matter whether it's in the tail or not. What matters is the height of the posterior density at one model versus another when you evaluate it at the data.
Yeah. Okay. So the first comment. I mean, this is in a way it's an in-sample exercise in the sense that you know, we're asking the question whether after estimating the model, whether, you know, the model produces simulated data from the model look like the data that we've used in the estimation. You know, we haven't done any out of sample exercise. You could take the QAR models and you know, see how well they perform out of sample. You can look at the DSG model and see how well a nonlinear versus a linear DSG model performs out of sample. But sort of, yeah, it's a different class of exercises. We've done some work, you know, in this on these issues, but you know, it wasn't in this presentation. And about Chris's point, I mean, I guess it's sort of, you know, trying to you know, comparing marginal data densities, I guess, across models. It's sort of it's a nice measure, but often it's sort of difficult to understand why one model is doing better than another model. And you know, one of the nice thing, I guess, about these predictive checks is that you can learn a little bit about dimensions in which you seem to be consistent with the data, and dimensions in which you're not consistent, in particular in situations in which it may be costly to specify you know, a whole set of alternative models.
So I must end this section. Maybe we should talk some more over coffee. We'll be back at 5:15.